Good afternoon, everyone. We are the last group to report the solution of ordinary differential equations. We have boundary value, shooting method, and finite difference method. I am Marian Pigingoni. We'll discuss about the boundary value. So we have objectives, define a boundary value problems, solve a boundary value problem given a general solution to differential equation. Now, the first thing we need to do is to define just what we mean by a boundary value problem. A boundary value problem for a given differential equation consists of finding a solution of the given differential equation subject to a given set of boundary conditions. A boundary condition is a prescription sum combinations of values of the unknown solution and its derivatives at more than one point. Kaning nga lesson is naagianan ni nato pag second year first sem, and I know naka-familiar na sad mo ani kung unsaon ni siya. If nakalimot mo, pwede ra sad ni ninyo tan-awon. So, the boundary value problem, a system of ordinary differential equations with solution and derivative values specified at more than one point. Most commonly, the solution and derivative kay nag-specified og mga boundaries or sets of conditions like ingani, y0 is equals to 1, y1 is equals to 3, y0 is equals to negative 2, y2 pi is equals to negative 2. Mga ingana nga conditions, mao na siya. Para masabtan jud nato, let's have an examples.
Hi, I'm Giovanni Abel. For today's video, we're going to show you the solution of ordinary differential equation, boundary value, and sample problems. So as we all know that boundary value problems contains differential equations in a set of boundary equations and evaluated of different points. Alright, let's start with example number 1. Example number 1. Find a solution to the boundary value problem y is equal to y quantity 0 is equal to 1, y quantity 1 is equal to 2. If we know y quantity of x is equal to c sub 1 e over r sub 1 x plus c sub 2 e over r sub 2 x is a general solution to the differential equations. Solutions. R squared is equal to r. R squared minus r is equal to 0. R is quantity r minus 1 is equal to 0. R is equal to 0. R minus 1 is equal to 0. 0 minus 1 is equal to 1. R is equal to 0. Y quantity x is equal to c sub 1 over e 0x plus c sub 2 e 1 over x e 1 e over 1x. So y quantity x is equal to c sub 1 plus c sub 2 over e x. 1 is equal to c sub 1 plus c sub 2 over e 0. 1 minus c sub 1 plus c sub 2. C sub 1 equals 1 minus c sub 2. 2 equals c sub 1 plus c sub 2 over e over 1. 2 minus c sub 1 plus c sub 2 over e. 2 equals 1 minus c sub 2 plus c sub 2 over e. 1 equals negative c sub 2 plus c sub 2 over e. 1 equals c sub 2 over e minus c sub 2. 1 is equal to c sub 2 quantity e minus 1 is equal to c sub 2 1 over e minus 1. C sub 1 equals 1 minus 1 over e minus 1. C sub 1 is equal to e minus 1 over e minus 1 minus 1 over e minus 1. C sub 1 is equal to e minus 1 minus 1 over e minus 1 is equal to c sub 1 minus e minus 2 over e sub 1. E minus 1 rather, sorry. Y quantity of x is equal to e minus 2 over e minus 1 plus 1 over e minus 1 over ex. The final answer is y quantity of x is equal to e minus 2 over e minus 1 plus e over e minus 1. That's the final answer. Thank you so much for listening.
Good day, I am Florian D.M. Daan. This is the example 2 about boundary value problems. So, determine the solution to the boundary value problem y double prime plus 2y is equal to 0. We're given two initial conditions of boundary conditions. So, y to 0 is equal to 1 and y to pi is equal to 0. So y double prime plus 2y is equal to 0. Since it is equal to 0, let's think about the characteristic equation. So it's r squared plus 2 is equal to 0. So solve for r. So transpose or subtract both sides by negative 2. So r squared plus 2 minus 2 is equal to 0 minus 2. Then r squared is equal to negative 2. And take the square root of both sides. So square root of r squared is equal to square root of negative 2. Since it is negative values, so we will be dealing with the imaginary values. So r is equal to 0 plus or minus of the square root of 2 times the imaginary number. So remembering when we get the imaginary roots of the characteristic equation, so we should do the sine or cosine equating. So our general solution will be y is equal to c1 times 1. So e to the power of 0 is equal to 1 man, so muna 1 cosine of square root of 2 times t plus the c2 sine square root of 2 times t. So boundary condition 1, y is to 0 is equal to 1. So 1 is equal to c1 cosine 0 plus c2 sine 0. So cosine 0 is equal to 1, then sine 0 is equal to 0 mo nang 1 c1 times 1 plus 0. So c1 is equal to 1. So bc2 y of pi is equal to 1. So 0 times 1 cosine of square root of 2 times pi plus c2 sine square root of 2 pi. So transpose nimo ang cosine square root of 2 pi, so mahimong negative cosine square root of 2 pi kana nasa white is equal to c2 sine square root of 2 pi. And then divide both sides by sine square root of 2 pi. So mana i-divide. Then mana nahimong negative cosine square root of 2 pi over sine of square root of 2 times pi is equal to c2. So we all know that cosine over sine is saman cotangent. So mahimong negative cotangent of square root of 2 pi, so equal to c2. Then substitute the value of c1 and c2, so mo ang final answer. Final answer is y is equal to cosine of square root of 2 times t plus cotangent of square root of 2 times pi times sine of square root of 2 times t. So that is the final answer.
The next topic is all about the shooting method. In numerical analysis, the shooting method is a method for solving a boundary value problem by reducing it to the system of an initial value problem. Roughly speaking, we shoot our trajectories in different directions until we find a trajectory that has the desired boundary value. So this is the illustration. Shooting method converts a boundary value problem to an initial value problem. A trial and error approach is then implemented to develop a solution for initial value version that satisfies the given boundary conditions. Let us convert the second order heat conduction equation to an IVP or to first order ODEs.
Here, I will demonstrate to you the shooting method with the second order ODE from heated rod problems. Our ODE is second derivation of T plus H prime times T alpha minus T is equals to 0, which is from the derivation of Author's law. Plug Fourier's law into the heat balance equation and divided through by K. And our boundaries conditions are T of 0 is equals to TA and TL is equals to TB, and is expressed as second order equation into two first order ODEs. We let Z as the derivation of T, and the derivation of Z is equals to H prime times T minus T alpha. Then substitute. D of Z over D of X is equals to 0.01 times T minus 20. To solve these equations, we required an initial values of Z. For this method, we guess a value, say Z of 0 is equals 10. Using a fourth order RK method with a step size of 2, we obtain a value at the end of interval of T of 10 is equals to 168.3797, which differs and obviously lesser than the expected value, which is T of 10 is equals to 200. So, we must make another guess. We say Z of 0 is equals 20 and perform the computation again. This time, we obtain T of 10 is equals to 285.8980, which is way greater than the expected values. So these are the values that we obtained. If Z of 0 is equals 10, then T of 10 is equals to 168.3797. Then, if Z of 0 is equals 20, then T of 10 is equals to 285.8980. And because the values are linearly related, as such, they can be used to compute the true value of Z of 0 that yields T of 10 is equals to 200. A linear interpolation formula can be used for this purpose. Let's say Z of 0 is equals to 10 plus 20 minus 10 over 285.8980 minus 168.3797 times 200 minus 168.797. Then we get the true value of Z of 0, which is 12.6907. Then these values can be used to determine the correct solution.
So, in this presentation, as you can see here, in the PowerPoint that I've been presented, is that I will explain to you the steps on how to solve shooting method. So as you can see here in the PowerPoint, this is the equation of the second order ODE is transformed into a system of two first order ODE. So step 1 is that reduce the second order ODE or BVP of equation to a system of first order ODE or IVP. Step 2 is that determine the initial value
The boundary value at the first point of the domain is known and is used as one initial value of the system. The additional initial value that required for solving the system is guessed. Step 3. The equivalent system of the initial value problem is then solved via Euler's method. So, what is Euler's method and how it works? So, the Euler's method is the first order method, which means that the local error or the error per step is proportional to the square of the step size, and the global error or error at a given time is proportional to the step size. RK2 method of RK4 method. However, in this course, only Euler's method shall be considered. Step 4. The solution obtained at the end point of the domain is compared with boundary condition. If the numerical solution is different from the boundary condition, the guessed initial value is changed, and the system is solved again. Step 5. If the result obtained from the second initial guess also differ from the boundary conditions, extrapolate the initial value using linear extrapolate formula. So this is the equation where the G1 is the first guess at initial slope, G2 is the second guess at initial slope, R1 is the final result at endpoint, R2 is the second result at the endpoint, and D is the desired value at the endpoint. The equivalent system of initial value problem is then solved via Euler's method.
For better understandings of what shooting method is, let's try one example. So here, the position x of a falling object of that time, t, is governed by this equation. 2 times d squared x over dt squared is equals to 9.8 minus 2 times dx over dt. With boundary conditions, x of 0 is equals to 0 and x of 20 equals to 800. Approximate the solution of the position x for each interior nodes by using a linear shooting method. Let's use the first initial guess z sub 0 equals to 5 and second initial guess z sub 0 equals to minus 5 and the letter h, which is the step size, equals to 5. So here, this is the equation and given from the problem. So here's the solution. The first step, let's rearrange our equation into our general form. Let's move 2 to the other side, and now the equation becomes 4.9 minus dx over dt. Now this is already in our general form. And then let's change our second order to first order. So let dx over dt is equals to z. And then we differentiate again. So we will have d squared x over d squared t is equals to dz over dt equals to 4.9 minus z. Okay, so from here we have two equations. So the first one will be our f1 and the second one will be our f2. After that, let h from timeline. We start with t is equals to 0 and the increment is equal to 5. So we have t sub 1 is equals to 5, t sub 2 is equals to 10, t sub 3 is equals to 15, and t sub 4 is equals to 20. Okay, if t equal to 0, we have x is equals to 0. So x equal to 0. And then the next one, when t is equals to 20, we have x is equals to 800. So x sub 4 is equals to 800. We are going to find the value for x sub 1, x sub 2, and x sub 3. Since we have two differential equations here, that's mean with three variables x, z, and t, so we need to solve by using system of Euler. The formula we have xi plus 1 equals to xi plus f1 equals to ti xi zi multiply with h. And then we have zi plus 1 equals to z plus zi plus f2 equals to ti xi zi multiplied also with h. And the last one, ti plus 1 is equals to ti plus h. So this is the formula of Euler for system. Now, let's start our calculation. So firstly, make sure you know when t is equals to 20, our x must be 800. So for the first calculation, let's start with our first initial guess. Exact is not equal to 5, so we have to solve our problem by using Sister Euler or Euler for system. And I present my answer in this table, and if we see when t equals to 20, our x is 72.5. This is far away from our condition. So we need to proceed to the next calculation, where we use the second initial guess, where our z is equals to minus 5. Here. To minus to minus 5. Again, we solve our problem. By using Euler for system, and I present my answer in this table. And when t is equals to 20, this is my x, where my x is over from our condition. Because of that, we need to use linear extrapolate to find the new initial guess. But before that, I just want to tell you that our z is equals to 5. This will be our g1. And our second z is equals to minus 5. This will be our g2. And answer from the first calculation here is 72.5. This is our R1. And the answer from the second calculation, or sa table, this will be our R2. So this is the formula for linear extrapolate. So let's substitute all the information that we have. So we start with G1 is equals to 5 plus G2 minus D1, that's mean minus 5. Minus 5 divided by R2 minus R1, so we have 2,622.5 minus 72.5 multiplied with D minus R1, so we have 800 minus 72.5.
So just by using our calculator, so our new initial guess z not is equals to 2.1471. So continue our calculation by using the new initial guess z is equals to 2.1471, and solving the same problem by using a system of order, and I present my answer in this table. So now I have 20 is equals to 20 to my
Finite difference method. So what is finite difference method? It is an approximate method for solving partial differential equations. It has been used to solve a wide range of problems, includes linear and nonlinear, time-dependent and dependent problems. So, how can we solve the finite difference method? First step in solving finite difference method is discretizing the domain. It means that the discretization of domain allows one to calculate approximate solutions over each subdomain rather than over the entire domain. The solutions on the subdomains are represented by continuous functions and the nodes of those subdomains. The second step to solve finite difference method is fulfilling the equations at discrete time points. It means that discrete time points is a time series consisting of a sequence of quantities. With this, we can obtain sample in the equation. The third step in solving finite difference method is replacing derivatives by finite differences. A finite difference method proceeds by replacing in the derivatives in the differential equations with finite difference approximations. This gives a large but finite algebraic system of equations to be solved in place of the differential equation. The last step in solving finite difference method is formulating a recursive algorithm. By formulating a recursive algorithm, we can obtain the result for the current input by applying simple operations to the returned value for the smaller input. So here are some examples of equations using finite difference method.
Here's another example for solving differential equation using the finite difference method. So this is the given problem statement. Approximate the solution of the initial value problem where second derivative of y minus 1 minus x over 5 y is equals to x, y1 is equals to 2, and is equals to y3 is equals to negative 1. On the interval 1 less than or equal to x less than or equal to 3. So put x sub n is equals to x plus nh, x equals to 1, h is equals to 0.5, and let y sub n be the calculated approximation for y sub n equals to y times x sub n. So we use 5 nodes here. So we divided into 5 die. So kani maning first, which is given 1. So kani di ay kay equidistant siya, meaning ang distance between each other is equal, which is 0.5 kani given siya 0.5. So dire 1 hantod dire sa x sub 1 is equal to 1.5, x sub 2 is equals to 2.0, x sub 3 is equals to 2.5, and x sub 4 is equals to 3, which is given sad ni siya. So ang pangitaon nato kaning tulo. Kanin na lang tulo kay kaning first o last given naman ni siya. So kaning tulo mo itong pangitaon. So we now use the central finite difference approximation kanitong gamiton, which is y sub I plus 1 minus 2 y sub I plus y sub I minus 1 with respect to delta x squared minus 1 minus x sub 1 over 5 y sub I is equals to x sub I where I 1 to 3. So, i-transpose ni siya. So, mo ni siya this gives y sub I plus 1 minus 2 plus 1 minus x sub I over 5 delta x squared y sub I plus y sub I plus 1 is equals to x sub I delta x squared. So, for katong first, for I1 first, kay mo ni siya, i-transpose ra ni nato y minus 2 plus 1 minus 1.5 over 5 times 0.5 squared y plus 1 plus y sub 2 equals to 1.5 times 0.5 squared, and for I equals to 2, y1 minus 2 plus 1 minus 2 over 5 times 0.5 squared, y squared, y sub 2 plus y sub 3 equals to 2 times 0.5 squared, and for I equals to 3, y sub 2 minus 2 plus 1 minus 2.5 over 5 times 0.5 squared, y sub 3 plus y sub 4 equals to 2.5 times 0.5 squared. So, i-transpose na siya para makuha ang inyong answer. So we set y equals to 2, y sub 4 equals to negative 1, and get the system of equations with the three unknowns, y sub 1 plus, y sub 1, y sub 2, y sub 3. So, this is the linear system. So, kaman mo tulo ka book, kay tulo man ka book equation. So, kani y sub 1, kani siya, mo ni siyang kanang answer or sa given diri nga equation. Mo na siya ang answer. So, parehasad sa uban sa y sub 2, y sub 3. So, mag-get na nimo ang answer kani using this equation. Negative 2.175 y sub 1 plus y sub 2 is equals to 1.625, which is kani. And sama po diri sa y sub 2. Y sub 1 minus na siya. 2.150 y sub 2 plus y sub 2. So, equals to 0.5 mo sa siya. Sa y sub 2 minus 2.125 y sub 3 is equals to 1.625. Imura dyan na siya i-transpose, i-calculate na siya, mag-get na ninyo ang answer. And the final answer is kaning 1, kani siya. Muna na siya ang answer sa ato ang unknown na equation, kaning y. So actually, when you solve this, any equation, you're going to get the kaning answer. I-transpose lang gihapon na siya. So, y sub 1 is equals to 0.5520, y sub 2 is equals to negative 0.4244, and y sub 3 is equals to negative 0.9644.
Good day, I am Delary Condales, and today I will give an example of finite method of difference. So, in this segment, we will going to look at the finite methods of the difference to solve boundaries values of ODs. In this particular method, I will just give you the background of it. The best way to show you how to find the difference method work for ODs is basically to check or go to examples. And I choose this differential equation, the second derivative of u over derivative of r squared plus 1 over r times derivative of u over derivative of r minus u over r squared is equals to 0. So let's put or assume that u of 2 is equals to 0.008 and the u of 6.5 is equals to 0.003. Let's expect that these two boundaries are given, so let's get the boundaries between 2 and 6.5. In fact, this is a differential equation which governs a partial method. And first, for us to get or easily get the equidistance or the different node, we will use the line method. At first dot or the node 1, we have r minus 2, and the last dot will be r equals to 6.5. So for us to get these two middle nodes, we will use the delta r equals to the last node or the number 4 nodes minus the first node, and it divide it by 3, so the answer will be 1.5. Then to get the middle nodes, we will use the number node plus the product of the delta r, and the answer of the node 2 is equals to 3.5, while the answer of the node 3 will be 5. Next, this will be the final diagram, in which node 1 we have 2, node 2 we have 3.5, node 3 we have 5, and node 4 equals 6.5. Now let's find u as a function of bar. So use 4 nodes to do the problem, which is equidistance or equal distance. In node 1, u1 is equals to use of 2 is equals to 0.008, and then the node 2 will be use of 3, and those will be the equation that will be substitute later. 2 use of 2 plus use of I over the delta r squared plus 1 over r squared times use of 3 minus use of 2, or the nodes of 3 minus nodes of 2 over the delta r minus use of 2, or the nodes of 2, r squared is equals to 0. Then after getting the equation, so it means let's substitute the given numbers. So use of 3 minus 2 use of 2 plus use of 1 is equals to the value of the delta r is equals to 1.5 squared, and I forget that there will be 2 here, plus 1 over 3.5 times node 3 minus use node 2 over 1.5 minus, then that's 1.5 squared, and I also forgot it, and use of 2 over 3.5 squared is equals to 0. And by this, the number or equals to this equation, and this equation will be continued by our co-members. And that's all. Thank you.
So this is the continuation. In the example, we are now on node 3. In node 3, I is equals to 3. The equation, u sub 4 minus 2 u sub 3 plus u sub 2 over delta r squared plus 1 over r sub 3 u sub 4 minus u sub 3 over delta r minus u sub 3 over r sub 3 squared is equals to 0. Substitute delta r to 1.5 and also substitute r sub 3 to 5. So by computing, we can now get 0.444 u sub 2 minus 1.0622 u sub 3 plus 0.5778 u sub 3 is equals to 0 as our third equation. And next is node 4. In node 4, we have I is equals to 4. And in node 4, the equation is u sub 4 is equals u multiplied by 6.5 is equals 0.003, and this is served as our fourth equation. In this, this is the part of diagonal method. We will use diagonal method in this by Thomas algorithm, or this is from Thomas algorithm, and by substituting and multiplying this, we can get u sub 1 is equals 0.008, u sub 2 is equals 0.005128, u sub 3 is equals 0.003778, and u sub 4 is equals 0.003. And this is what the graph looks like. And we can now go on to exact solution. The formula we have, u is equals c sub 1 r plus c sub 2 over r. We have here u of 2 is equals 0.008 and u of 6.5 is equals to 0.003. In here, we have u is equals 9.150 times 10 to the power of negative 5r plus 0.015634 over r, and u of 3.5 is equals to 0.004871, and the u of 5 is also equals to 0.0035843. In u of 3.5, we have 6.65%, while in the u of 5, we have 5.11%, and this is our exact solution. And that would be all. Thank you.